All right. Thanks everyone for joining. I'm very excited to introduce our speaker today in the third session of the Berkeley Programming Systems Summer 2020 seminar series. So our speaker today is Rachit Nigam from Cornell University, who is a second-year PhD student working with AD and Samson on high-level programming models for hardware architecture design. In Rachit's own words, before being violently thrust into the world of computer architecture, he worked on programming languages and built many compilers for JavaScript. So that's pretty cool. He is famous on Twitter for boasting the highly controversial Twitter handle no types, which seems to be in direct conflict with the topic of today's talk. So I'm looking forward to seeing which side Rachit actually believes in. So I think today's talk is based on the topic of Rachit's upcoming PLDI 2020 paper, which, if I'm not mistaken, Rachit submitted when he had a broken wrist and was still able to submit on time. Yeah, that's pretty cool. That's really impressive. So really looking forward to hearing about Rachit's work on predictable accelerator design with time-sensitive affine types. Thanks a lot, Rachit, for speaking today, and thanks everyone else for joining. And over to you, Rachit.
Great, thank you for having me, Ron. And yeah, I'll be talking about all of this work. It's done with a lot of really talented and other incredible people who helped me both create the system and also help me submit in time. I didn't do it alone. A lot of people helped me do this. If you're curious about some of this work and some of its offshoot, you can go to this link, capra.cs.cornell.edu/Dahlia. And it has sort of a web-based compiler for our language. You don't need to install anything, and all of our research material. Okay, so before we start, a bit about myself. As Ron mentioned, I'm a second year, soon to be a third year PhD student. And I work on the intersection of computer architecture and programming languages. My general pitch for my research is that I work in computer architecture only to sneak in sort of programming languages concepts into this area. And I work with Adrian Sampson, who's my advisor, who's also in this call, and he's generally interested in similar sort of problems. He looks very serious here. My guess is because he's looking at all the various theses from Berkeley and wondering where the hell is this tower. I don't know the answer to this, but seems deep in thought. But all right, let's move on to the talk. So meet our protagonist. This is Ada, and she's a software developer, and she's had a great new idea for a cryptocurrency that's going to be backed by matrix computations. And it's going to solve the two hardest problems in computing. It's going to solve cryptocurrencies, and it's going to solve machine learning. But a key question on Ada's mind is how to efficiently build a mining platform for her cryptocurrency. And the two things she cares about is the cost of building this platform, so how much money she pours in and how much time she puts into this, and the efficiency of the computations that run on this mining platform. So her choices include using a CPU, which is sort of ubiquitous and super easy to program. You can have your choice of languages, and you can write CPU programs, and they run reasonably fast. You can also use GPUs, which use a specialized programming model, and they can parallelize certain kinds of kernels really, really well. The ultimate choice that Ada has is using an ASIC or a custom chip that you can fabricate by like writing down a hardware design and pouring a few $100,000 into like a silicon fabrication company, and you get chips. And this is really the most efficient way of doing things because you're designing a circuit that can implement your specific computation, and you can do it really fast. But it's also really expensive in both the sort of the amount of time required, the effort required, and the monetary cost. A trade-off between all of these design choices is using an FPGA, or a field programmable gate array, which is a kind of funky reconfigurable architecture that can be programmed to run certain kinds of circuits and run them really, really fast. And a great thing about FPGAs is that they're available on public clouds like AWS. You can go buy an F1 instance on AWS, and you can just write your FPGA programs and run them, and it all sort of works out without having to do this tedious task of fabricating your own chip. You can still get massive speedups. So this talk is about Ada's journey, how she discovers FPGAs as a programmable fabric, her delight in finding about a new programming model that allows her to write software programs that can be compiled into hardware designs, her frustrations with some of the unpredictability that this programming model has, and finally, how a language and a type system can actually help Ada combat some of these problems. Our specific research that we contributed in this work is talking about the unpredictability of the programming model that I'll tell you guys about, as well as the language that we designed to combat some of these issues. But first, let's talk about FPGAs. So there are many ways to go down from a hardware design to an FPGA. You can have a notional hardware design and you want to run it on an FPGA. Your first choice is using a traditional hardware description language or an HDL. And those languages sort of operate at the level of gates, wires, and clock cycles. And you have to write down your programs very carefully, and you have to sort of push it through a compiler that generates something that runs on an FPGA. So let's take a look at some HDL code. You don't have to understand what this code is doing at all. I'm just going to highlight a few parts of this code that are interesting and weird. So first, there's this statement always at +edge clock, which refers to the fact that this design, this component runs at the positive edge of the clock cycle, which means your designs inherently have a notion of time in a way that software programs don't have a notion of time. Software programs have a notion of ordering, right? Program statements run before each other, but they don't have to deal with like precise timing of your design. But in hardware design, time is real. Time is something you have to care about. And if you don't care about it, you're going to have bad hardware designs. There's also these weird, funky looking assignment statements that have semantics that are quite unlike what software languages have. So the semantics of assignment in hardware description languages is often that you set up all your assignments at the start of your clock, and at the end of your clock, you can they all get sort of committed, and then they run at the end of the clock, which is quite different from what you're used to in software languages, where you write a statement and it's immediately executed, and every other statement after that can observe the changes. This is a different snippet of code that shows how we compose in hardware description land. So we have some module, and the key thing to note here is that we're taking what look like sort of arguments to this module or this function, and we're putting in some variables. And those variables actually correspond to physical wires that are put into the hardware module. And that module can then send out signals on those wires, and that's how you communicate across your design. So the basic model of composition is still structural. So you have to think about hardware wires and so on. So that's one choice. Another choice Ada has is using the modern reincarnation of hardware description languages, which often come embedded in software languages like Scala and Python, and provide sort of powerful meta-programming capabilities that are supposed to make your life easier. So one example of such a modern HDL is Berkeley's sort of famous Chisel programming language, which allows you to write essentially Scala programs that allow you to generate hardware designs, right? The great thing, seemingly, about HDLs in this reincarnation is you can use high-level constructs. You can use for loops, you can use tabulate, you can even use an anonymous function. So we've solved the abstraction problem of hardware description, except not quite, because these designs are still elaborated into hardware circuits. So when you write a for loop in one of these languages, what you're doing is defining a generator or a meta program that creates various hardware modules and connects the wires. At the end of the day, if you want to figure out if your design is correct or not, and figure out what its sort of semantics is and what it's computing, you still have to think about structural components like clock cycles, and you have to still think about like hardware modules. So that's the other choice, right? And finally, Ada can use something called high-level synthesis, or HLS. And this is what HLS programs look like. So if you're surprised, this looks exactly like a C++ program, because it is, in fact, a C++ program. And what HLS purports to do is write software programs, and will compile your software programs into good hardware designs. And that is sort of a really radical way of designing hardware. For a really long time, we've designed hardware using hardware description languages. And when we write those programs, we have to really think about the timing behavior, the structure, the clock, and so on. But if there's a magic way of taking software programs and turning into hardware design, that could really open up hardware design to people from backgrounds like mine, where we mostly develop software programs before jumping into this. And to really understand how radical this programming model is, you have to realize the level of abstraction that HLS provides is fundamentally different from HDLs. HDLs are fundamentally circuit specifications. They specify circuits that have timing and structure behavior. Whereas HLS programs are computational specifications. You can use your for loops, your conditionals, and those get compiled into hardware modules. Your correctness properties, you can reason at the computational level instead of the circuit level. Now, obviously, C++ and other software languages are quite complicated. And when you work with these languages in sort of the HLS plan, you don't get to use all of the funky features that they have. For example, there's no equivalent of malloc or memory allocation that C++ allows, where you can sort of dynamically allocate new memory. Because in a hardware design, you have to think about how much memory your program is going to use. You have to fabricate a circuit, or you have to like tell the FPGA how much memory you're using, and that's it. That's all of the memory you're going to get, no more. You can't create anymore. You also can't use dynamic features like breaks and method calls because they're very sort of control heavy. And one of the things that make hardware design really fast is reduction of control. So you don't want to use these features. So you're really programming with some sort of restricted subset of C++. But at the end of the day, for someone like Ada, this is still maybe a reasonable trade-off because you get to write software programs that end up in high-performance hardware designs. And really, that's still profoundly changing the level of abstraction you have. So Ada is going to jump into the land of HLS programming, and she's going to try to design her first accelerator. So she wants to design her super secret accelerator, and unsurprisingly, it's going to be a matrix multiply kernel. So I'm sure all of you have seen this before. It's sort of 3-loopness, some computation, assignment done, right? Quite straightforward. And notionally, if you think of the kind of hardware it's going to generate, we have a few memories for inputs and outputs. We have the core sort of computational component of our kernel in the form of a multiplier that multiplies things, followed by a reduction pipeline or an accumulation pipeline that accumulates the results of summing things and writes it to local register. Finally, we have a write back stage where we write the values of the register back to an output memory. So Ada builds this design, she runs them, and they actually run. Like you can write this program today and you will get a hardware design. But what she sees are modest speedups, 10 to 20% over like a CPU baseline. And she's wondering what is she missing that these other people have been able to use to get anywhere from 2 orders of magnitude to 15,000x speed up in their designs when they use FPGAs. And the key thing Ada realizes is that she hasn't exposed any parallelism in her design. And a way to do sort of exposing the parallelism in an FPGA design implies that you're going to make something called an area latency trade-off, which means that you're going to have more processing elements. You're going to have more multipliers and adders, and that's going to take up more resources on your FPGA. So that's going to utilize more sort of hardware resources that your FPGA gives you access to, which is generally a bad thing. But in return, you get to use, you get to see speedups, you get latency benefits, you get to have a hardware design that can perform more computations in a smaller amount of time. And these area latency trade-offs are a key part of hardware design. You don't build hardware designs just to have something that is functionally correct. You want something that can compute as many things as possible in as little time as possible. So these area latency trade-offs are quite important. So Ada goes in and she picks the obvious part in her design to parallelize. So the innermost loop doesn't have a whole lot of dependencies. In general, matrix multiply kernels have a lot of parallelism, so she can just go and do that. And what she wants to do is create duplicate copies of her multipliers to process multiple elements in parallel. And HLS compilers recognize that this kind of parallelism is very common and very abundant. And they give access to something called a pragma, or a code annotation, that the HLS compiler can use to say, okay, I have the pragma HLS unroll with some factor. It's going to take the loop body, and it's going to create multiple copies of the loop body. And when it goes into the HLS compiler knows that that means it has to create more processing elements and sort of parallelize the design. So next, Ada really wants to understand how changing the unrolling factor or increasing the parallelism factor of her design affects her area and her latency. So on our left, we have this resource called LUT, or lookup tables, which directly correspond to area. So every time you see LUT in the stock, you should think area. And on the right, we have runtime, which corresponds to latency. And in general, Ada expects the area to get worse as she increases the parallelism factor of her design, while the runtime gets better. But the actual numbers she gets are quite weird. The area is sort of mostly flatline, and the runtime actually seems to get worse as you increase the parallelism factor. These are not made up numbers. You can actually go and run these designs on AWS's F1 instances, and you'll see these results. And so Ada's confused. What's going on here? Well, Ada can go call her hardware design friend, and they'll say, okay, think really carefully about the architecture you're building, specifically this part of your hardware design where you're expecting the memory to be feeding 3 values into each individual multiplier every cycle, which means all of them are operating in parallel. Well, turns out FPGA memories are quite unlike processor memories. Processor memories are sort of incredibly complicated hierarchies of memories that allow sort of lots of parallelism implicitly in the way you access them. But FPGA memories are super low-level physical circuits where you're really working with the lowest abstraction over memory. Unfortunately, this means that when you actually try to do something like this, you're going to hit a constraint of FPGA memories. The constraint is that every clock cycle, you only get to read or write 1 value at a time, which means when you build this design, the HLS compiler is going to silently insert extra control logic in the form of something called a multiplexer. And what the multiplexer does is that it decides which one of the multipliers is going to get a value this cycle. Unfortunately for Ada, this means that she'll have designs where she has increased the parallelism factor, she has more processing elements, but the designs actually run slower because there's all this extra logic that's saying, okay, this cycle, this multiplier runs, that cycle, that multiplier runs, and so on. And this is the key form of unpredictability that I want to talk to you about today. This unpredictability is the feeling of like the HLS compiler not really following the intent of what Ada wrote, right? She wrote HLS unroll factor 3 because she wanted 3-way parallelism in her design. And then the HLS compiler almost maliciously complied with her. It almost said that like, I'll give you more processing elements because that's what you requested, but I'm going to add all of this extra logic that's going to totally go against the grain of what you wanted me to do, right? And this unpredictability makes it really hard to do area latency trade-offs, which again are a key part of hardware design. You want good hardware designs that sort of explore those trade-offs.
Had a lib count in Terrier like a year ago. That was
sorry, you're very quiet. I can't hear you.
Closed that issue when CPL came in.
Still very quiet. Better. Is there a question or?
If there is a question and your mic isn't working, you can put it in the group chat and one of us will read it out.
Okay. Should I forge forward and you guys can call out the question whenever it's ready?
Yeah, let's do that. But actually, I have a question too. So adding in this multiplexer, shouldn't that make the size go even bigger? The plot doesn't seem to reflect that. Is there something I'm missing?
Yeah, that's a reasonable question. It's actually quite hard to explain all of the trends that go on in this graph. You'll also notice that it sort of jumps down for a while when you go to the point 8. And that's almost precisely the point that I'm making with unpredictability. Explaining any of these graphs requires sort of talking about second and third order effects, right? There's not just the multiplexers, there's also the various kinds of routing that happens when you have these kinds of weird decisions you're making. So the point I want you to take away from this graph is not that there's like a normal trend that you can explain. It's precisely that you can't explain any of these graph points without delving too deep into sort of all of the second and third order effects that come when you design HLS programs. A key thing to realize is compiling to FPGA is a sort of an inherently random process. We use a lot of random algorithms to solve NP-hard problems because that's what a lot of compilation is for FPGAs. So there's a lot of sort of problems that show up in that form as well. Is the other question also ready? I can answer that.
I think it was a misclick, so we can just keep going.
Sounds good. Okay. Okay, so thankfully for Ada, this specific problem isn't new. This problem of extra muxes being silently inserted isn't new. And there are many people who have sort of run into this before, and Ada can go find like forum answers. And eventually she realizes the way to solve this problem is using yet another code annotation. This code annotation is called pragma partition, and it operates on memories. And what it does is it creates physical partitions for sort of logical memories. So more precisely, you have some logical memory. Let's say you have some memory A, and you can create physical partitions that back that memory. So you have your memory A that's actually backed by 3 physical memories. Each of these memories sort of contain a different disjoint subset of the elements in the logical memory A. And what this allows HLS compilers to do, or sort of just hardware designs to generally do, is access elements in sort of a parallel fashion. The way the elements are distributed from the logical memory to the physical partitions is in a round robin way. So its memory sort of elements are striped across the physical partitions that allow you to access adjacent elements in parallel. So specifically, the reason memory partitions are good is because instead of connecting your processing elements or multipliers into logical memories, you can directly go and hook up the wires into the physical memory. And now each partition is serving exactly one multiplier, and all of them can execute in parallel. So this means that writing this design down, Ada sort of expects that her design, her parallelism to be better exposed, right? And because there's this physicality associated to partitions and like multipliers together, Ada is going to do another experiment where she's going to change the unrolling and the partitioning factor in lockstep. So for example, the point 2 in this graph is going to have partitioning factor 2 and unrolling factor 2. And again, we have the area on our left and runtime on the right. And this time, we're hoping this works better, right? Unfortunately, the numbers this time are even more weird. Okay, so the runtime does seem to go down. Ada gets almost a 4x speed up on her sort of largest design. But the area numbers are all over the place. They go up and then they suddenly jump down and they suddenly go up, right? Weirdly, there's a subset of points that seem to have some sort of predictable behavior where increasing the parallelism factor seems to generally have the runtime, while the area generally increases in sort of the amount that having more multipliers you would expect that to have. And all of these points align with powers of 2, and we all know computers like powers of 2, so maybe that's the issue. Unfortunately, that's not quite the right answer. What Ada is actually running into is that she has a memory that has 512 elements, and she has 3 partitions, and 512 is not evenly divided by 3, which means when she tries to create these partitions, she's going to have mismatched partition sizes, which means certain partitions will have fewer elements. And again, the HLS compiler has to deal with this problem. It's not going to error out. It's sort of a stoic warrior. It will solve your problems, and it's going to insert extra logic yet again. And now the logic will say, okay, if I'm a processing element that's connected to one of these mismatched partitions, and I have reached the end of my partition size, I'm going to sort of stop executing now. And this extra logic is actually quite costly. It's not cheap. So if you look at the difference between the 0.7 and 0.8, it's almost a 60% extra area. And you'll also notice on your right that the runtime for 0.7 is actually worse than the runtime for 0.8. And again, if somehow Ada could just magically think about the subset of points that seem to behave nicely, that would be really good. One thing to notice about these specific points I've highlighted is that they almost always form like a local minima of both runtime and the area. So Ada jumped into the world of HLS programming, and she built her first design, and she pushed it through an HLS compiler, and it really worked. And she was really excited about it. But then she keeps running into these like fine print issues where she has to just like carefully line up these things. The HLS compiler never tells her. It's always trying to solve her problems and going against her intentions. Maybe you're hoping there's some like black book of magic that Ada can read and become the best HLS designer out there. But that's really not the problem. These issues are just a symptom of a deeper problem. And the problem is that the language that it is working with is not capturing the timing and the resource constraints of the programming model. FPGAs have physical resources, right? Memories have certain behaviors. Memories can't serve more than one read or write every cycle. And memories are physical. You can't just pass them and copy them like variables in a normal C program. And that's really at the heart of the problem. If there's anything you take from this talk, it's that if you build languages that compile to hardware and you don't think about their resource and timing behavior, you're going to have unpredictability in your design. That's a fundamental part of the language. But okay, maybe we should step out. Maybe this is just a C++ problem, right? C++ is a pretty gnarly language and there's a lot of corners. Maybe if we design a new language from the ground up, okay, I completely messed up that transition. I'm going to do this again. There's an actual cost to the unpredictability that Ada has been running into, right? Ada has 16 designs, which is roughly 32 hours of compilation on an FPGA. Compiling down to an FPGA is actually quite a costly process. Again, because you're solving these NP-hard problems, it's going to take a lot of time. And what's worth noting is that something like a matrix multiply kernel is actually quite small. As her designs get bigger, this time will only go up. On the other hand, if Ada had some access to like a magic oracle that could tell her that only these 4 designs are going to be worth even worrying about because they make some sort of predictable trade-off, then Ada could have cut her time down to 8 hours. And as your design spaces get bigger and your sort of kernels get more complicated, these numbers are going to be sort of quite a lot bigger. Going back to the question of is C++ the issue, we can look at a different research language. This is a language out of Stanford. It's called Spatial. And the cool thing about Spatial is that it was built bottom up. People like hardware engineers who care about language design went in and they were like, okay, how do we build good abstractions such that we can compile them easily and have sort of a sane language? And it comes with like various cool features like automatic memory partitioning, right? So instead of writing down by hand what the partitions in your memory should be, you just write your parallel accesses and the compiler will sort of infer the best partitioning scheme. And maybe we can go and hope that this automatic partitioning scheme would actually be good. Unfortunately, we sort of tried another experiment. Again, we sort of plotted the normalized resource usage on the y-axis, normalized against no unrolling. And on the x-axis, we have the unrolling factor. And then we have 3 resources, LUTs, PRAMs, the SPs. LUTs are sort of corresponding to the area. And again, you'll notice that all of the points that are sort of not aligned with the sizes of the memories are going to make fundamentally bad trade-offs. None of these points are even worth considering because they're just fundamentally bad trade-offs, and we shouldn't be thinking about them. So again, timing and resource constraints are at the heart of this problem. If you don't think about them, you're going to build languages that are going to have these predictability problems. So, okay, that's good. But going back to this question of having a magical oracle, right? That seems really hard. We set out to build something similar. We wanted to build a language that would enable predictable sort of exploration of hardware designs, and we built this language called Dahlia. That purports to allow predictable accelerator design. So let's think about how Dahlia works and why it can help with some of these problems. Dahlia is its own language. It has its own syntax and its own funky kind of type checker that I'm going to talk about. And it eventually compiles down to H-less C++, and it adds all of the pragmas you need to add. And then we push it through an H-less toolchain that can generate hardware designs. So let's take a look at some Dahlia code. So Dahlia has memories. It uses this funky sort of OCaml-ish syntax where you can declare a memory. So you have your memory M1. It's going to have 10 elements of type float. And you can read and write values. So let x equals to M1 blah sort of reads the value. And the other statement writes the value 1 into index 1. This generates the kind of hardware you would expect. So there's sort of a register that's reading a value from M1, and there's a constant generator or something that's writing the value 1 into M1, right? And the key question Dahlia asks when it sees a physical resource being used multiple times, in this case, a memory, it asks, can these accesses run in parallel? Can this read and write run in parallel? And from what we know about FPGA memories, we know that this is going to be false. And because of this, we're going to have sort of an unpredictable trade-off in the general case because the H-less compiler will have to sort of insert extra logic to enable this. Because of this, Dahlia will error out saying affine resource M1 has already been used in this context. So what does this cryptic affine resource thing mean? So Dahlia is something called an affine type system. And the sort of crux of an affine type system is that it only allows at most one use of a variable. So specifically, we have a declaration of M1 here, and we have 2 uses. And because, again, 2 is more than 1, so that's not good for an affine type system. And that's why Dahlia gives this error, affine resource M1 has been already used in this context. So every time you see the word affine in the sort of type systems literature, you should think at most one use of a variable. The reason Dahlia asked this question in the first place is because semicolon means something special to H-less compilers. For Dahlia, we use the word unordered composition for semicolons. And that's because H-less compilers are actually free to parallelize programs composed with a semicolon arbitrarily as long as they respect data flow. And for Dahlia, this means that the read and the write may run in parallel, which means it has to consume the affine resource that M1 denotes. But this program should be representable. In fact, if you write this program in H-less C++, the H-less compilers will do some sort of like squeezing and changing, and it'll generate hardware. To denote the kind of hardware the HLS compiler generates, we have a different kind of composition operator, and it's called ordered composition. And what it means is that the two program statements are going to run sequentially. And this means that you can renew the affine resource. So that means that before the triple dash, M1 can be used at most once. And after the triple dash, M1 can be used at most once. This language of triple dashes and semicolons, these composition operators, allows Dahlia to reason about the temporally exclusive use of resources. And that's what's fundamental to hardware design. You use the same resources multiple times, but you sort of coordinate them temporally such that their uses never conflict. So in this program, Dahlia will allow A and B to share the same resources because A and B run sequentially with respect to each other. But C is composed in parallel to both of them, and Dahlia will say C can't use resources from either A or B because, again, C doesn't know how long it takes A or B to run. So Dahlia has to say that C, you're not allowed to use any of the resources that occur in these program statements. Next, Dahlia has for loops because all interesting programs must have some looping behavior, and you can unroll these loops. Okay, so back in HLS land, writing this program will make an unpredictable trade-off. It's going to create more processing elements, but you'll never see sort of the speed up you were expecting. And because of that reason, Dahlia will again give this affine resource error. And that's because morally for Dahlia, this program is equivalent to this other program where we've hand unrolled the inner loop. And we've composed all of the statements with semicolons. Again, because we're composing with semicolon, we're implying that the reads into M1 might run in parallel. And again, that is not allowed for predictability reasons. Dahlia also has partitioning capabilities on memories. We call it bank, but you can just think of it as various memory partitions. And you can take a memory and say, I want to create 3 banks on this memory. And this program, if you recall, again, from HLS land, is making a predictable trade-off. It's sort of making designs that are going to directly connect the processing elements to the partitions and are going to be fast because of that. So because of that, Dahlia has to say, okay, this sort of partitioning scheme is going to be valid. And the way Dahlia says that this is going to be a valid program is, again, it reasons about this morally equivalent program where you enroll everything. It looks at the access expressions and it decides that all of these expressions touch disjoint parts of the logical memory. Specifically, they each touch a distinct memory partition, which again means there's no affine resource error. So memory partitions become the unit of affine reasoning. But weirdly, now we've gotten into a place where we're trying to reason about properties of expressions in programming languages, and that's always a dangerous territory. So to think about this, let's look at this different program that is almost equivalent, where we have 2 for loops and we have iterators I and j. And let's think about what an HLS compiler needs to do when you unroll one of these iterators. Well, the HLS compiler has to look at this expression and sort of reason about the space, the iteration space of I and j, and say that, okay, this is going to touch disjoint elements of the memory, of the partitions that we're working with. But in general, it has to reason about properties of arbitrary functions. Like you can have any function there over I and j. You can have I times I, and you have to reason about the values it touches. And because of sort of the complexity of analyzing arbitrary program expressions, the analysis that the HLS compiler is doing is fundamentally going to be unpredictable. And that's because sort of, again, you have to prove properties of arbitrary program expressions. You can actually do an experiment where you write a simple expression like 3 times I plus j, and then you can like do +0 or ×1, and the HLS compiler will fall over its feet. You'll have really good designs, and then you'll have really bad designs. So instead of relying on such an unpredictable analysis, Dahlia actually simply rejects these programs. Dahlia only allows memory accesses to be through sort of straightforward iterations. And if you don't use straightforward iterators, it'll tell you that it cannot parallelize a dynamic access pattern. But clearly, this particular access pattern is parallelizable. HLS compilers, if you give them precisely this expression, they will actually parallelize your design pretty well. And to denote sort of the world of predictably parallelizable iteration sequences versus the unpredictable ones, Dahlia uses something called memory views to denote which one of the iteration patterns you're using. So to work with memory views, you take sort of a normal physical memory and you describe a logical view over it. So it's still working with the same physical memory, but you now have described a unique iteration pattern over that memory. And this view corresponds directly to the extra hardware that you need to implement the specific iteration pattern. So this iteration pattern 2 times I requires like a multiplier and times and sort of the constant generator 2 and so on. So that's the hardware cost that the view captures automatically. And for Dahlia and the type checker, it acts as a proof that certain access patterns can be parallelized predictably. So going into our example again, we're going to use a special kind of view called a suffix view. And the restriction on the suffix view is that you can only offset by the banking factor. So the banking factor on memory M1 is 3, and we're going to offset by 3 times I. And the reason we have this restriction is because this specific kind of offset is actually quite cheap to implement in hardware. You don't have to generate sort of crazy amounts of hardware, and you can just have a simple sort of offset that changes the band you're accessing. Finally, once you have a view, you, instead of accessing the physical memory, access the view. And this corresponds to you sort of using the iteration pattern of the view. And because Dahlia has now separated the creation of the iteration pattern from the use of the iteration pattern, it can sort of prove that the unrolling of this iteration pattern is going to be safe. When Dahlia is done type checking, it's going to rewrite it to sort of this lower level access expression. Dahlia also has something called a shift view. And shift views allow offsetting by arbitrary expressions. And shift views are going to be much, much costlier than suffix view exactly because of this reason, because you have an arbitrary access expression that will require some arbitrary amounts of hardware logic. In this specific way, sort of views act as documentation in the code or sort of focus points in the code where the programmer can go in and figure out which parts of the code are the most worth changing. So turning a shift view into a suffix view is a big enough win, while turning sort of a suffix view into direct memory access wouldn't actually get you that much because suffix views are not that costly compared to shift views. Okay, so Dahlia has a lot of other features that we didn't get to talk about. We have support for sort of logical pipelines, reduction pipelines, and we have various other kinds of memory views that allow parallelizing different complex access patterns. And we also have sort of a formalism that formalizes a core calculus for Dahlia and proves a type soundness theorem that says that if your program type checks, then the program will never try to access the same memory partition between 2 logical timestamps. This is all well and good, but what about Ada? What Dahlia has been up till now is that it can sort of tell you that certain programs are going to be rejected. And Ada gets a bunch of error messages that try to explain to her why certain things are not good. But is that really enough of a value add to learn a new language? Maybe. So in the type systems universe, we have this adage. It says, well-typed programs cannot go wrong. And this is really a statement about the kinds of programs the type system accepts. In our world, we want to show that well-typed programs make a predictable trade-off. But predictability is this like weird, subjective, amorphous property. There's no real easy way to formalize this. And we have to show this empirically. So what we're going to do is perform something called a design space exploration experiment. So what you do in a design space exploration or DSE experiment is you take a kernel. So we're going to take block matrix multiply. You enumerate a bunch of designs. So we enumerated 32,000 designs by varying the unrolling factors and the partitioning factors and some other things that Dahlia supports. And then we're going to run something called estimation. Okay, so compiling down to an FPGA is really, really costly. If we do this for 32,000 designs, it would take a long, long time. So ageless compilers have something called estimation mode, where they quickly generate a design and they estimate the amount of resources it's going to take. So that's what we're going to use. And for sort of straightforward kernels like block matrix multiply, we're going to have reasonable results. Next, we're going to map the LUTs used, or the area on the y-axis, and the latency of the design in terms of cycles on the x-axis. And this is the kind of space we get with all of these points. So a key thing to notice here is that even for a very simple design, like block matrix multiply, there's a wide variety of sort of regimes you can end up with. You can end up with on the sort of left and bottom hand side, where you have designs that are running really fast and not taking up a whole lot of resources, while you can have designs on the top right side, which are like super slow and also run really slow. And this is really sort of the predictability problem of ageless design. when you have a design and you make some trade-offs, you do some unrolling and partitioning, you can arbitrarily end up in any of these points. No one is ever guiding you because, again, our HLS compiler is like a stoic warrior. It will always try to solve the constraints you give it. And sometimes it'll solve it so badly that it'll end up in one of those bad points. Next, we calculated the Pareto optimal points with respect to FPGA resources and the runtime of the design. So we have 4 FPGA resources, but we only map LUTs and latency because we have a 2-dimensional graph. And that's why we have a few Pareto points that are sort of on the inside of the normal expected Pareto frontier. Finally, we took all of the points and we ran the Dahlia type checker on the entire design space. And we plotted the points that Dahlia accepts. Specifically, Dahlia accepts 354 or 1.1% of the entire design space. But this design space is not going to be really useful unless you're sort of accepting any of the Pareto optimal points. So next, we also plot the Pareto optimal points Dahlia accepts, 15 out of 56. And that's really the value add that Dahlia brings to the table. Instead of working with these massive, complicated design spaces, you enumerate them and you run type checking on them. Type checking is much, much cheaper than both compilation and estimation. And within a few hours, you can have a much more restricted subspace that is going to have predictable trade-offs and is going to hopefully contain some of these Pareto optimum points. So that's sort of empirically our argument for why you should use Dahlia. We also
Can I chip
performed
in
a
with a
bunch of other
question?
qualitative. Yes, go for it.
These 15 programs, these all will do what the programmer intended in the programming language, right? In terms of input output.
That's sort of yes, all of these programs are functionally the same. The only thing that is different about them is their performance and area characteristics.
Okay, thanks.
Yeah, so again, functional correctness is one part of the problem, but that's not the entire thing, right? You're trading off area and space to get designs that can compute as many things as possible while taking up as few resources as possible. So that's what the design space exploration experiment is all about. We also performed a bunch of qualitative studies with various other kernels and talked about sort of the kind of frontiers and the subspaces they generate. You can read about it in the paper. I'm going to specifically focus on a programming, sort of qualitatively programming problem of one of these kernels. So here we have a 2D stencil, and it has four loops and then a bunch of accesses and then a multiplication, right? And you can go write this design, push it through an HLS program or HLS compiler, and it'll work. And then you're like, okay, how do I optimize? Well, you have 4 choices for unrolling. You can unroll any of these 4 loops. You have 2 partitioning choices. How much do you partition each one of those memories? And very quickly, your sort of design space is going to be quite massive, even for sort of a very simple, very straightforward, very common case of a 2D stencil. Here's a Dahlia program. And again, we have 4 loops. We create a view. And again, we have an axis, and we've turned sort of the single-dimensional memory into a 2-dimensional memory. And again, we have 4 choices for unrolling. So how does Dahlia restrict your choices in this case? Well, I'll say the first 2 loops cannot really be unrolled predictably, because when you create this view, you're creating multiple windows of computation. And some of these windows will overlap, which means that your computation is not predictably parallelized. The HLS compiler will have to do some complicated analysis, and at the end of the day, it's going to add extra control logic, which will stall your processing elements. So don't even bother unrolling those. Next, those 2 can be unrolled, and as soon as you unroll them, Dahlia will say, okay, you must partition these 2 memories, because again, if you don't partition them, why are you even bothering with sort of unrolling these designs? You're not going to see any speed ups. So very quickly, your sort of massive design space turns into 2 or 3 points in this case. Not exactly 2 or 3 points, but a few points. So I'd like to sort of close this talk by talking some of the future work in this area, specifically talking to the programming languages and the architecture crowd, and telling you why all of you should be friends. So we've been looking at Dahlia programs that have concrete banking and unrolling factors, right? We write bank 3, unroll 4, and so on. One thing I really want to do with Dahlia is create a notion of resource polymorphism, where you can have abstract resource numbers. And what Dahlia does is it looks at all of the constraints that are induced between these abstract parameters. And it returns to you a set of valid configuration options. And what this will enable is that instead of sort of taking a big design space and then running the Dahlia type checker on each individual point, you can just have one program and it's going to immediately generate all of the valid configurations and you're done. You don't even need to run the type checker. So that seems like a cool thing to build. The second problem is this fundamental problem of modularity, which is really hard in the world of hardware design. So here's sort of a straightforward function. Don't really worry about what it's doing. It's a general dot product, and it takes two memories inputs, and then you call the dot product. Okay, straightforward and simple. We can modularize this code. Next, we can have some banking and unrolling in the dot product. And okay, this is sort of weird because A and B are physical resources. But again, we can say that A and B will need exactly 5 banks or something. And that will be good enough for us to call the dot product. But what happens if we call the dot product in an unrolled context? Well, unrolling says that I need to run dot product in parallel, but dot product is a function. Does it refer to like one instance, or is there like one hardware module, or is there 2 hardware modules? Even if I have 2 hardware modules, how many banks do A and B need to do? So quickly it sort of becomes complicated. And again, the fundamental problem is that we haven't talked about the compositionality of timing and resource behaviors of programs. And we have to think about those really hard and figure out how we can compose those things naturally. If we don't do that, we're going to sort of have these really incomposable programs. In HLS land, you generally can't compose programs like this. You have to either inline them or sort of do other kinds of tricks. Finally, Dahlia is a first sort of step towards building a fully predictable hardware stack. So it sits in the middle of this high-level languages and hardware description land, where it brings up some of the abstractions of hardware description languages up to high level without sort of sacrificing the expressiveness of high-level languages. But there's a lot of other languages that live in this stack. There's Netlist, there's HDLs, there's hardware languages, there's all sort of stuff. And it's really interesting to think about what kinds of languages can describe the abstractions and the physical constraints of these sort of levels of abstraction. And a key thing that having these languages will enable us to do is conveying good error messages and sort of domain principles to programmers that work at a high level. So common problems in sort of building hardware is you don't have a design that fits your sort of area that you're working with, or it doesn't meet the timing. And if you're working at an HLS level, when you eventually get the Verilog and then you push it and 3 days later it comes back and it's like timing not met, and you're like, what do I do with this? And so that if we have languages that capture sort of the physical constraints of things that can never be, we can maybe communicate more effectively about what's going on down the stack as well. So that was my talk. Thank you all for coming and listening. And I hope all of you can help me bring predictability from languages down to LUTs. Again, that is the link where all of our research stuff is hosted. I'll take questions now.
Thanks, Rachit. Great talk.
Thank you.
You, Rachit.
We have a lot of time for questions. I guess if you have any questions, feel free to just unmute yourself and ask the question to Rachit. And also perhaps like mention who you are, introduce yourself so that Rachit knows who's asking the question.
Hi, Rachit. I'm Pranav. I'm a master's student at Berkeley. I had a quick question about some of the programs that you guys were expressing in Dahlia. So these ones, I think, like at least from the optimizations that you were showing, are more like, unrollings and that kind of stuff, right? Were there any that had, different optimization models, like something that wasn't just unrolling, that was more expressible in Dahlia?
Yeah, that's a good question. So there are sort of many different ways of optimizing these kinds of programs. I have 2 responses. One is that HLS compilers are good at optimizing only certain kinds of programs, right? So the kinds of programs that are really good at optimizing are data flow heavy programs where you can pipeline really aggressively and you can sort of parallelize and duplicate things really aggressively. So Dahlia supports unrolling as the main form of reasoning principles to sort of eliminate certain designs that it knows are going to be unpredictable. It does not, at a sort of first class level reason about pipelining, because so there are certain programs that will be much more optimized if you pipeline them effectively. And the reason it's super hard to reason about pipelining is because now you don't have to just think about memories, you also have to think about like all of the physical resources you're using. So for example, in a for loop, like we have up here in the top left, the multiplier is now going to represent sort of one physical resource that is temporally distributed. And reasoning about sort of the predictability of that and how the HLS compiler is going to predictably parallelize that multiplier seems hard. That's something we want to do for future work, but we haven't tackled yet. There are other kinds of programs as well, like, okay, the stencil program. The best way to optimize the stencil program is building line buffers, which allow you to reuse data locally. So as you do your computation, you save like a small window of elements you've seen, and you can read and write those values sort of in a local register or something. The thing about, again, these special kinds of optimization patterns is that they're not directly expressible in C++. The way you instantiate reuse buffers is that you either use a completely different HLS tool that can think about stencil computations, or you sort of use one of these template classes that say, okay, I know what I'm doing, please instantiate a reuse buffer. And that's the other kind of parallelism that needs to be tackled to express like other domains of sort of optimization strategies. But those are also not handled by Dahlia.
Sweet, yeah, thanks. It was a great talk, by the way.
Thank you.
Hey, Rachit. This is Sankha.
Hey.
I'm a PhD student at University of Maryland. Great talk.
Nice to meet you.
So I had a couple of questions. So this type system works because the user provides annotations in forms of bank and unrolling, right? So is there any way to automatically infer those annotations? And also, can you have something like a cost function that says maximize the resources so that you can infer the bank and unroll factor?
Yeah, so that's also a good question. There are two answers to this. One is that because these are talking about sort of non-functional properties of the program, you never have to put bank and unroll, right? Like you can always read your program unannotated and it has the same functional behavior. Change that happens when you add banking and unrolling is sort of the resource properties. So that doesn't directly affect sort of the problem of annotation, right? You always have to add these annotations. The question of can you automatically infer them? But there's a lot of work in this area where people go and build tools where you do automatic insertion, right? There was this paper at DAC, I think this year, which showed that you can have this DSE tool that just automatically and randomly adds unrolling and banking and port numbers and so on, and it can find like the designs. I would say Dahlia is sort of orthogonal to that. Like you can certainly use tools like that. You can automatically insert those pragmas. And the value add for Dahlia there is that now your DSE tool that's using some like complicated machine learning model can immediately reject certain designs because they know that the type checker said that this is not going to work out. So if you want to do sort of that automatic annotation, you can do it. But the problem that Dahlia specifically is solving is that certain design and certain subspaces don't make any sense. Don't even bother exploring them. So that's the answer to your second, I think, question. And there was a third question of like, how can we sort of automatically maximize the resource usage? That is, again, an interesting question. The fundamental problem that HLS compilers are tackling with when they add all of this extra logic is that memories are mutable, right? HLS compilers have a lot of freedom in creating more multipliers or more adders or more registers, but memories are immutable. If you do a memory access that represents a memory location that is like sitting in the FPGA on the side, and you better access that, you don't just like willy-nilly sort of duplicate them. So in some sense, you have maximized the resources. The bottleneck is memories, and that's why Dahlia is sort of focused towards memory quite heavily. Hopefully that answers your questions, but if you have follow-up, go for it.
No, they answer everything. Thanks.
Thank you.
So we have some questions in the chat. So a little bit of a backlog. I'll read one out. So Matt asks, great talk. Out of curiosity, would you happen to have any insights on using the type system to improve predictability or debuggability compared to Verilog, e.g. avoiding metastability, as in invalid designs with clock domain crossings, accidentally inferred latches, etc.?
Yeah, that's a good question. I think that's quite hard. First of all, just the general problem of figuring out, sort of disentangling the intent of a programmer from what Verilog compilers and all of these compilers are doing today when you build those hardware designs. The specific problem I think Matt is talking about is that sometimes you can write Verilog designs where you expected a certain hardware resource to be instantiated, and it instead instantiates something else that completely screws over your design. I think the problem there, specifically sort of the reason insights from Dahlia don't directly apply there is because when you write a Verilog program, a multiplier represents a physical resource. In HLS programs, there's a distinction between logical resources. So like in this program, we have 12 multipliers, right? And those can be implemented with 1 multiplier or 6 multipliers or 12 multipliers or anything in the middle, right? So that flexibility is what sort of the type system is talking about. These specific problems of I instantiated the wrong element are really hard and really important to solve, but I think the right place to solve those are languages like Chisel or like Hard Camel or something. For example, I know like Jane Street uses this language called Hard Camel that's embedded in a camel, and they have a policy of like, if I have any warning, I'm going to take that as an error. And that's how they get around these problem of inferred latches specifically. There's some clever language design work and clever sort of research to be done there. I'm not sure if I know sort of direct applications of affine type systems there.
Matt says thanks. Maybe we should prioritize voice questions, but if no one has a question, there's still a backlog, so I can read the next one. I'll give a few seconds. All right, so Alexander asks, can you use FPGA to speed up enumeration and checking?
Interesting question. So I'm going to assume this means that, okay, you have a design space, 32,000 design points. It's not easy or fast to type check these programs. For example, like type checking 32,000 points with Dahlia takes about 8 hours of computational time. I ran it on like multiple cores with GNU parallel, so it took 40 minutes. That's for 2 reasons. One, my implementation is sort of in Scala and highly unoptimized, which means it's slow, but it's sort of, in general, it's going to be sort of a slow problem to solve, right? So the question is, can we use FPGAs to automatically enumerate them and then somehow like run the compiler in the FPGA? Seems really hard because, look, we're designing like matrix multiply kernels on FPGA, and that's hard. Putting an entire compiler in an FPGA or like a type checker is also going to be really hard. But the reason this question excites me is that maybe 5 years from now, or 10 years from now, this sort of software-directed hardware design languages will enable us to build compilers that can automate these problems really, really fast, right? Like the problem here is that a lot of these tools have been traditionally used by hardware engineers, and they're focused towards hardware designers and their needs. But we, the software people, are now like, we want to build hardware designs now. FPGAs are like widely available, and they promise sort of speed ups that we've never seen before. So maybe we can build like languages that will allow us to express that. The final sort of legit answer of how do you speed up enumeration and checking is having a notion of resource polymorphism. So if sort of you build this resource polymorphism and you say like, M can only be between 0 and 12, M is limited to being 4 and 3 and 1 and 6, and then N puts various constraints on M. Those constraints together, you can ship off to like an ILP and an LP solver, and it will give you all of the configuration. So that's the sort of short-term path I see to speeding up enumeration and checking, because then the design points you get are correct by construction. Hopefully that answers your question, Alexander.
I have a question.
Yeah.
So if I have a memory that's being used in 2 different places in the data path, let's imagine I'm reading at some point, then I've got some pipeline, and then I'm writing to that same memory. And I might, typically design that by interleaving the reads and writes such that my pipeline length has to be odd so that my reads and writes kind of interleave naturally. Could I express, how would I go about expressing that kind of constraint? Would it infer it for me, or would I have to tell it that?
I see. So you have, okay, so step back. Generally, you want to express pipelining schemes where you use memories in a way so that you don't have conflicts on various partitions, right? Like a very simple example is like I of a of I equals to a of I minus 1 plus or times 2 or something, right? This pattern is not sort of trivially parallelizable, but it's really trivially pipelinable. And the question is, how do you pipeline this, and how do you sort of infer good banking strategies for it? Dahlia in its current form, again, doesn't reason about pipelining of memories because it sort of gets into this complicated problem of resource reasoning. The answer to how do you infer good sort of banking strategies, the algorithm I briefly showed out that Spatial uses is this algorithm called tracebank that came out of Cornell. And it uses this scheme where it tries to sort of symbolically figure out what partitioning scheme you want to use. I think in general, extending Dahlia to automatically at least verify partitioning schemes against pipelining is sort of a natural next step. And we're thinking about how to express those problems as well. Again, so early work has limitations.
Cool, thank you.
Thank you.
Maybe I can read the next question from the chat. It was Saeed who says, thanks for the great talk. I was wondering if this can be used to address side channel vulnerabilities like Spectre and use the notion of time to make sure it does not depend on the secrets as well. Like have a kind of balanced resource usage instead of speed up.
Oh, that's a very interesting question, Saeed. A few answers to these. One, there is, so I'm not involved directly in this project, but there's a group of projects led by Andrew Myers and his PhD student, Drew, who are thinking about how to build sort of hardware-software stacks where you can reason about complicated, what are called information flow control properties, where you can provably have both an architecture and a language and an ISA that says no side channels at all. And they've built this architecture called Hyperflow that actually provably does not have timing channels, and they have an ISA for it that again says, as long as your program type checks in this ISA, you're not going to have any side channels, timing-based side channels. The question of, okay, how do you do side channel analysis in this program, and how do you figure out resource use? How do you make resource usage patterns constant enough that you can't have side channels on FPGA? That's an interesting question. I think the first problem of how do you stop like what are called implicit flows. So like you have a secret conditional and then you execute one part of your program or the other depending on that conditional. These kinds of problems are sort of, I don't want to say solved, but are already kind of very far ahead. They're like the whole field of information flow control has tried to solve and address these kinds of problems. There's this paper from last year, I think, that has information flow control secure HLS tools, again, from Cornell, that I can send you guys if you're interested. There's totally a way you can build the affine type system to basically force each branch of a program to use exactly the same number of resources. You can use something called a linear type system or an extension to a linear type system that says you have to use the resource exactly the same number of times as this other branch. So that might help with the resource usage patterns on the branches. But again, this is an interesting question that would be fun to explore in the future.
Said says thanks in chat. And there's also another question in the chat, probably the last one right now that's in the chat, which is from Karthik. And Karthik says, I wonder if implementing this as an EDSL in a language that has native support for affine types like Rust is viable.
Yeah, good question, Karthik. So I have lied through the entire talk. Dahlia doesn't use a purely affine type system. It uses sort of an extension called a bounded linear logic based type system that allows you to reason about properties that say, I can use my memory at most k times, because again, real FPGA memories don't have the restriction that you can only do one read or write every cycle. It's like you can do two because you have two memory ports, and Dahlia in general supports reasoning about arbitrary multi-ported memories. So that's one reason why embedding sort of languages like Dahlia into Rust will not work sort of directly. It's also problems with sort of borrow checker. So the Rust borrow checker is sort of this incredibly complicated beast that is hard to understand. And we don't care about the borrow checking part of the problem, right? It's good to have, certainly, but that's not the problem we were solving. So we built this language to hone in on the exact problem we want to solve. The path to making languages like Dahlia, or the ideas in Dahlia, sort of more widely applicable, I would personally go about and sort of implement an EDSL in C++ or something, because that's what most of the hardware engineers who use HLS today actually use. They like work with languages in C++, and they have immense sort of systems that are built to work with C++. So that would be my first choice. Of course, it doesn't give you all of the niceties of Rust, but you know, you have to make Faustian bargains to make research impactful.
Thanks. Makes sense. Thanks. That's what Karthik says in the chat. I also have a question for Rachit. So yeah, firstly, great talk. Thanks for that. I was wondering, so a lot of the problems that you described have maybe some analogous issues even in the software world when you're trying to, let's say, parallelize software, or maybe to maximize the performance you can get from things like caches, right? And when you deal with maybe thinking about how much you want to unroll your loop and how you want to organize memory and so on and so forth, and there's been a ton of work in programming languages for, I guess, parallelizing software. Are any of the lessons that you've learned in this work maybe something that could be applied even to the software world, or do you see any connections or anything that you might have borrowed from that field that you want to comment on?
Yeah, that's a great question, Ron. This is sort of a question that's close to my heart because I am sort of fundamentally a software guy. Although I would point out that these are, in some sense, software programs. These are just being compiled to a different hardware target. And that's usually the way I think about the lessons I learned from Dahlia when I want to apply them to new domains. So, okay, the first problem of general purpose processors have various kinds of characteristics, and certain kinds of programs work really well on them. So can we use sort of resource constrained language that can reason about cache models or something to improve performance and make it more predictable? I think that is perhaps the hardest question to answer among all of the things I will lay out next. And that's because sort of processors aren't just piles of caches, right? They have superscalar sort of pipelines, and they have out of order execution, and those things really make it really challenging to model these behaviors. The place I think we have some room to design these languages are sort of the super restrictive parts, right? Like in Dahlia, we identified that memories are key. Memories you can't mess with because they're finite in a way that everything else isn't. And maybe there's sort of hope that you can model caches in that way, because caches, again, memory is fundamental to performance, and maybe there's some stuff there. I would expect to start with like DSLs before I jump into a general language like C. Like maybe stencil computations would be a good place to start, I think, because they have sort of sane sort of parallelization schemes that you can think about. Halide is a great example of like what you can do when you have good language design in that area. So general purpose processors, I would start with sort of DSLs, and I would start with memories. The second answer is I also care about programming sort of hardware efficient, energy efficient hardware architectures. And that kind of work goes into funky VLIW sort of DSP architectures. Okay, I said two acronyms. So VLIW is very long instruction word, which is like this funky architecture where you get to pack many instructions into one and execute all of them at once. And DSPs are digital signal processors. So sort of every time you take a picture or you do like real-time filters on your videos, your phone is running a DSP inside, or several DSPs. And the way you program DSPs today is you handwrite a kernel that has these like swizzle patterns and all these various crazy custom instructions that allow you to best use sort of the resources on a DSP. And the reason this is really exciting is because DSPs don't have out-of-order pipelines. They don't have all of the craziness of memory hierarchies that normal processors have. And that's a place where you can actually model the architecture in a type system or in a language. So that's a particular problem I am working with a colleague, Alexa Manhattan, and we're working sort of taking a synthesis approach to this problem. But sort of follow-up question I want to ask with that problem is how can we use a type system to model these things? The final sort of general place, sorry, I'm answering this question for a long time, but this is, I love this question. The final place, I think we have room to think about type systems and sort of how we can use modeling, their modeling capabilities is using sort of CGRAs, which are these reconfigurable architectures that sit in the middle of like FPGAs and CPUs. So they have like, instead of having very, very fine-grained things like logic tables that you modify on an FPGA, you can actually have like full Ps, like you can have multipliers and adders and like matrix multipliers or something, right? And the hard problem of CGRAs from a PL perspective is programming them. Programming them is really hard because you have to coordinate the movement of data, you have to coordinate the use of resources, and you have to coordinate sort of the timing of various things. And that is a place where I think type systems can be really successful, right? There's all of this literature on like something like session types or something that talk about exchange of data. There's all of this research on affine type systems that talk about resources. And I think a cool place to apply all of those ideas that are like, in my opinion, maybe hard to motivate in the software world, but have natural analogs in hardware design. That's where you should sort of do type systems research. Right? Like if you're doing a crazy type system, hardware people probably have a use for it. So you should, that's why you should do hardware design with type system design. Hopefully that long answer had some sort of insights.
Yeah, absolutely. Those are great thoughts. Thanks a lot for those comments. And I think in the chat, Matt has a wild idea as a follow-up to the software applications question. Matt says, perhaps diagnosing false sharing, such as unintentionally using the same cache line across threads without the intent to exchange data between them, which is pretty bad for performance. Perhaps this could have a potential overlap with some of the techniques in the memory partitioning analysis in the affine type system of Dahlia.
Yeah, that's a cool idea. There's a lot of really cool dynamic fault sharing research too, which you would have to compete against, but maybe you can do something that sort of goes hand in hand. It's an interesting idea.
Cool. Thanks for that question, Matt. Are there any other questions? If there's no other questions, I guess we can wrap up. This was a great talk and we had some really great questions. So I really enjoyed the session. Thanks a lot, Rachit, for this amazing talk. And thanks everyone who joined in for attending and for all your questions. I really appreciate it. You'll applause for Rachit again. Thanks a lot for taking the time to present today.
Thank you. Thank you for having me. It was great talking about this.
Absolutely.
I will see you all one day when
Yep.
it's not so
When we have
distant.
Yep.
Bye now.
Bye-bye.